Hi, this is Boyoung Ri from Professor Jinung Kim's group. I have researched the phase transitions of a two-dimensional membrane assembled with new types of ceramide. So I will introduce the ceramide field and briefly discuss the objective and results of my research. First of all, ceramides are composed of a sphingosine base as a backbone with an amide linked to one acyl chain. Ceramides play the most important role in maintaining the skin barrier function. This skin barrier means the function to prevent our body from exogenous substances and significant water loss. The main skin barrier is the lipid matrix in the outermost layer of the epidermis, the stratum corneum. In detail, the stratum corneum has a structure similar to a brick and mortar array, which is composed of a rigid multilamellar lipid matrix with flattened dead cell corneocytes and intercellular lipid lamellae. The stratum corneum is a 9 to 13 micrometer thick rigid tissue consisting of 15 to 30 layers of corneocytes embedded in intercellular lipid lamellae. The only continuous structure, intercellular lipid lamellae, has a lower as the primary pathway for the diffusion of substances into the body, and it is most important for the skin barrier function. Intercellular lipid lamellae comprise ceramide, cholesterol, and free fatty acid in an approximately equal molar ratio. Out of these components, ceramide is the most important because it makes up around 14% of the lipid lamellae. Namely, ceramide deficiency can lead to difficulty retaining water and induce dry skin and lipid barrier abnormalities, which can cause various skin diseases, such as atopic dermatitis. Ceramides are classified into more than 16 types depending on the combination of 5 types of fatty acids and 4 types of sphingosine base derivatives. The chemical structure of ceramides determined the lipid lamellar morphology and the lateral packing structure. The ceramide subclasses with non-hydroxyl and alpha-hydroxyl fatty acids are known to form a short period phase rather than a long period phase for lipid packing. In addition, the ceramide NS, non-hydroxy sphingosine, has orthorhombic or hexagonal chain packing depending on the chain length, and ceramide NS with short chains results in denser lateral packing than that with long chains. However, phytosphingosine subclasses such as ceramide NP and steroyl phytosphingosine lead to denser packing, which lowers stratum corneum permeability, thus resulting in a more robust skin barrier performance. As numerous studies on ceramide have been conducted, their applicability in skincare is enormous. In fact, different types of ceramides exist in the human skin. Nevertheless, fundamental studies on how they affect the formation of lateral packing between intercellular lipids have not been reported, because ceramides especially have more effect on the lateral packing than other stratum corneal lipids. To figure out the effect of packing behavior for lateral structure of unknown types of ceramides is essential to understand the skin barrier function. In addition, there are many studies being conducted on high concentration ceramide hydration and stabilization technologies to overcome the limitations of ceramides, which have low solubility and high crystallinity in water. Furthermore, because natural ceramides are very expensive, research on the development of pseudoceramide is also ongoing. So, I used the Langmuir-Blaser technique to understand the lateral structure and surface arrangement of unknown types of ceramides. Langmuir-Blaser technique is a device that shows the behavior of phase transition through the surface pressure increase compared to reduction of area when pressure is applied. In fact, patterning and film deposition techniques using the Langmuir-Blaser have been widely studied, and many previous studies have been conducted, such as the lateral arrangement in monolayers based on the composition of ceramide and cholesterol, and the differences in structure depending on types of fatty acids of ceramide. So, I investigated the structural characteristics and behavior of phase transition of two new types of ceramides on the molecular assembly based on ceramide MP, which has good lateral packing by using the Langmuir-Blaser method. Briefly, I will discuss the results of my research. In my study, I used two types of ceramide. One is CuRC, which stands for ceramide with an ultra-long chain, and the other is CEMP, which contains acyl chains in both the N and 1 positions of sphingoside base. I assembled monolayers of these ceramides and analyzed their characteristics. The result indicated a favorable ordering and well compacting of lipids in the CuRC assembled membrane, while the CEMP assembled membrane showed disturbed parallel lipid packing. Moreover, these results were induced by the differences in the structure of the ceramides. The cycle isotome shows the strong chain packing of CuRC by the freely jointed chain between hydrophobic chains. These phenomena were confirmed through the graph plotted with elastic modulus and fluorescence images at various pressures. Finally, I checked the lateral membrane structure using a time-dependent wettability test. The result indicated that in the CuRC case, the hydrophilic heads were hidden due to the well-packed hydrophobic chain, while the hydrophilic heads of CEMP were exposed because of the lying alignment. Thank you for listening my presentation.